In software development, there's this constant battle, right? You want pure, unadulterated performance, but you also need rock-solid security. So how do you get both? How do you build something that's blazingly fast but also completely safe? Well, that's the exact question we're tackling today by putting two absolute titans, C++ and Rust, head-to-head. And we're going to do it by looking at their security weak points.
Okay, so before we can even begin to compare these two, we got to get on the same page about a really key concept, the attack surface. The easiest way to think about it is like this. Imagine your software is a house. The attack surface is basically all the doors, all the windows, the chimney, maybe a doggy door you forgot about. It's every single spot a burglar could try to get in. So the bigger that surface, well, the more chances an attacker has to cause trouble.
All right, let's start with the legend itself, C++. I mean, for decades, this has been the language for anything that needs serious performance. We're talking game engines, entire operating systems, you name it. And its whole philosophy is built on one idea. Give the developer absolute power and direct control over the computer's hardware, especially its memory.
And that right there, that total control, is what makes C++ so incredibly powerful. But, and this is a big but, it begs a really important question. What's the catch? What's the hidden cost that comes with all that freedom?
Well, that cost is memory management. See, by giving developers the keys to the entire kingdom, C++ essentially asks them to walk through a minefield. And even the absolute best, most experienced programmers can make one tiny little mistake that can blow up into a massive security hole.
So let's talk about one of the most classic and frankly devastating vulnerabilities. The buffer overflow. It's pretty much what it sounds like. You're trying to stuff way too much data into a box that just isn't big enough. And this isn't some academic theoretical problem. Nope. A buffer overflow was the exact vulnerability used in that 2019 WhatsApp attack, letting hackers install spyware on people's phones with nothing more than a phone call.
And these overflows come in a few nasty flavors. Think of it like pouring too much water into a glass. If it's a stack-based overflow, that water spills over and can actually rewrite a function's return address, letting an attacker hijack your program's flow. A heap-based one can mess up the very system that manages memory. And as you can see, sometimes all it takes is a single extra byte, and off by one error, to corrupt critical data and cause a catastrophe. Okay, next up, we have a much sneakier bug called a use after free. This is what happens when your program tries to use a piece of memory that it's already finished with and has given back to the system. My favorite analogy for this is, it's like dialing an old friend's phone number, but they moved, and the number was already reassigned. You have no idea who or what is going to pick up on the other end.
The way this attack works is just dangerously simple. Step 1, the program frees some memory. Step 2, a pointer to that now invalid memory location gets left behind. We call that a dangling pointer. Then, later on, the code follows that old pointer and starts reading or writing, but it could be accessing totally different data, maybe even malicious code that an attacker cleverly placed right there.
So really, it all boils down to this fundamental trade-off. The very thing that gives C++ its incredible speed, that direct hands-on memory control, is the exact same thing that opens the door to its most dangerous security flaws. The safety of the program rests almost 100% on the shoulders of the developer to be perfect every single time. But this is where the story gets really interesting, because Rust enters the scene, and it approaches this whole problem from a completely different angle. It asks, what if the developer didn't have to be perfect? What if the language itself could be a guardian, protecting you from these mistakes? And that's Rust's entire philosophy in a nutshell. Safety is not optional. It shouldn't be an afterthought. The revolutionary idea here is that the compiler, the thing that turns your code into an actual program, can be your security partner. It's designed from the ground up to find and stop these memory bugs before your code can even run. The magic behind this is something called the ownership model. Now, the core rule is actually pretty simple. Every single piece of data in Rust has one and only one owner. And as soon as that owner is finished with the data, Rust cleans it up automatically. This strict set of rules, which the compiler enforces relentlessly, just wipes out entire classes of memory bugs. And when you put them side by side, you can really see the fundamental shift here. With C++, the developer has to constantly juggle memory lifetimes in their head. With Rust, the compiler does it for you. It's a move from relying on human discipline, which, let's be honest, can fail, to guaranteeing safety right in the language's design itself.
And the payoff is huge. Because the compiler is so strict about ownership, it becomes literally impossible in safe Rust code to have a use-after free error, or a dangling pointer, or another nasty one called a double free. It even takes these guarantees into the super complex world of multi-threaded programming to prevent data races. The compiler just won't let you build it.
Okay, so we've got the two philosophies down. C++ is all about power, even if it comes with risk. Rust is all about safety, guaranteed by design. So now let's put them head-to-head on a few specific things to see how this all plays out in the real world.
Remember those buffer overflows we talked about? Well, here's exactly how Rust shuts them down. In C++, if you try to access an array out of bounds, it often just does it, silently. That's how overflows happen. In Rust? No way. By default, it checks every single time. It'll either stop the program cold, or even better, it forces the programmer to explicitly handle the case where there might be nothing there. Silent overflows just become a thing of the past.
And this safety-first mindset goes all the way into concurrency. Writing code that does multiple things at once is famously difficult. And it often leads to these horrible bugs called data races, where different threads step on each other's toes. In C++, you have to manage this manually with locks. In Rust, the compiler uses special markers, send and sync, to prove at compile time that your code is safe. It simply will not compile if there's a risk of a data race.
Even something like error handling shows this huge philosophical divide. C++ tends to use exceptions, which are powerful, but it can be easy to forget to catch one or to just ignore it. Rust uses a special type called result, which basically packages up both the success and the failure possibilities. And the compiler forces you to deal with both. You literally cannot compile your code if you ignore a potential error.
So when you pull back and you look at the big picture, it becomes incredibly clear. For these entire categories of critical security bugs, buffer overflows, use-after free, data races, that have been a thorn in the side of C++ developers for decades, Rust just eliminates the risk. Not by hoping for better programmers, but by changing the rules of the game at a fundamental level.
So what's the big takeaway from all this? It's that C++ gives you mind-bending performance and flexibility, but it puts the heavy burden of security entirely on the developer. Rust comes along and says, you can have that top-tier performance, but safety is going to be the default, not an extra. It provides those guarantees right at compile time, making it an incredibly robust choice for building the critical systems we all rely on.
And that really leaves us with a final, fascinating question to think about. As our world gets more and more digital, and as security threats get more and more sophisticated, is this trade-off the future? Are we seeing a shift away from demanding human perfection and toward building languages that guarantee safety from the start? It's a pretty profound change in how we think about building our digital world.